Hey everyone, I'm Tim Pullman. I'm a software engineer at Sonar, and today I want to show you how we map the multiverse of your code base. Every time you write an if statement in your code, you basically create two alternative universes depending on which code path the execution takes. And things can look very different in these universes. And of course, every time you add another condition to your code, you create another universe or two. And so it becomes this big pile of different alternative universes of what could happen in your code. Because we don't know what actually happens, right? We're doing static analysis, so we analyze your code before it runs, but we can make assumptions. And we use a technique called symbolic execution to create a map of that multiverse of code paths. And we take a look at that multiverse, or at that map, and try to spot if we find anything that looks a bit off or could be a problem. But let's make it concrete and take a look at an example. This piece of code is actual production code from Microsoft. This is part of the .NET Runtime codebase, very important codebase. And yeah, as I said, this is production code. This is live right now. You can check it out on GitHub if you want. So this code looks nice, but it has a bug. And yeah, we reported this bug when we found it with our analyzer. It has not been fixed yet, so you can still take a look. But yeah, so let me show you what is wrong with it. And then we take a look at how our analyzer did spot this problem. This is part of the class SqlMoney, which is basically holding a value, a money value. And this is stored in an internal field called _value. And the method is toInt64, which is basically supposed to convert that value into a long, so a different format, which means it needs to do some math, needs to do some calculation, and then it needs to do some rounding to get the correct result. And in the rounding, there's a slight problem, as we will see in a moment. So the first line is the calculation. And basically, to simplify, let's just assume it multiplies the value by 10. It's not quite what is happening here, but for simplicity, let's just assume it's multiplying the value by 10. And later it wants to divide that value by 10 again to get the correct value, the correct size again. And however, well, for that it needs to do some rounding, because these are integers or longs, integer values, so no comma. And for the rounding, it needs to do some extra calculation. So it starts here by checking if the value is positive or negative and storing the result in this variable called fpositive. And then the next step is, of course, the modulo operation, which is basically we take the value, we divide it by 10, we take the remainder and store it in this variable. Makes sense, right? Then there's the actual division by 10, and then there's the rounding. And the rounding is, of course, based on the remainder. If the remainder is equal or greater to 5, we need to round up. And if not, we automatically already round it down because of how integer calculation works, right? Integer division works. So, of course, we need an extra case for negative numbers because, well, negative numbers need to be rounded down if the remainder is bigger 5 and not up. And this looks all perfectly normal and reasonable, except there's a slight problem over here. And that is the modulo operator, because the modulo operator in math is not actually strictly defined. What is not strictly defined about it is how it operates on the negative values. And different programming languages implement this differently. So in Python, a negative value, modulo 10, would result in a positive remainder. However, in C#, it keeps the sign. So a negative number, modulo 10, will actually result in a negative remainder. And this is what's happening here. So if value is negative, remainder will actually be negative, and therefore can never be equal or greater 5. Let's take a look at a concrete number. So if we pass in minus 2.6 here, and as I said, we simplify and say this just multiplies by 10, then we get minus 26 for value. And if value is negative, so this is false, and the remainder now is minus 6, not plus 6, minus 6, because how C# treats the modulo operator. Value gets divided by 10, so it becomes minus 2. And, well, remainder is -6 now, so it's definitely not equal or greater 5, so it never enters this if, and therefore returns -2. But, well, as you can see, -2.6 should be rounded to -3, of course. So this is a bug, very clearly, but it's pretty tricky to spot because you need to know the details of how the modulo operator works and then look at all of this code and what it actually does. It's not very easy to spot, so I don't blame the developer who implemented this. But I find it very interesting that our analyzer can detect this. And this is how the analyzer reports the problem. So you can see it underlines the f positive check in the inner if and says that it always evaluates to true and that the else is actually unreachable. So the analyzer is like, there's something wrong here. This part of the code is not reachable. It, of course, doesn't really understand the method. It doesn't know what the method is or the intent of the method. It doesn't know what it's supposed to be. Like, it doesn't understand what toInt64 means and makes any assumptions based on that. But it takes a look at the structure of the code and figures out this code path is never reachable. This is surely a problem, right? Either it's a problem or we can just get rid of it if this is intended, because then it's unneeded. So the analyzer highlights this. And this is very powerful. And I want to give you a bit of insight on how the analyzer finds this and how it detects this. So we create together now the map of the multiverse of this piece of code. As I said, we use what is called symbolic execution. And what it means is that basically we have an engine that simulates the execution of your code. But instead of using concrete values and just trying different numbers, like let's throw 2 in here, 2.6 in here, and -2.6, and 0, and 5, that would, of course, be madness. That would just mean we need to execute your code. We don't do that, but we use, instead of concrete values, we use symbolic values. And symbolic values are basically classes of values or categories of values. So, for example, positive numbers or negative numbers, or like a range of numbers. For bools, it's a bit easier because a bool only has 2 possible values, true and false. So we actually use the concrete values. But for numbers, we create ranges and stuff like that. And we have a few other things we do for symbolic values, which are not relevant for this example, so I'll skip over them. But here we only need number ranges and bools, basically. So as I said, symbolic execution, our engine is stepping through the code and is simulating the execution. So it just starts at the top as natural, and it takes a look at the line 3 and says, this doesn't tell me anything really. I don't know what the value of underscore value, the field, is. There's some math happening, but an unknown number, some math, the result is still unknown. I don't know what's going on. So it just goes on to the next line and sees if it can find something interesting here. And it does, because here we have a condition, value equals or greater 0. And now the engine is like, okay, that's a condition. There's only 2 possibilities here. Either the condition is true or it's false. There's no third state. So maybe that's reasonable to analyze. Let's just take a look. Let's take an assumption for now. Let's just say the condition is true and see what is the consequence of that. What are the results? What happens if this condition is true? And so it creates a new state. And that state is basically value is equal or greater 0 and all the consequences that come from that. The first one, of course, is that the variable f positive will have the value true, because that's what the code does here. If this condition is true, then f positive is true. Cool. Next line, now interesting, under the assumption that value is positive, we actually can say something about this line. We can actually learn something here, because, well, if value is positive and we modulo by 10, then result must be positive as well. And it's modulo 10, so it cannot be bigger than 9. So the remainder must be in the range of 0 to 9. Hey, cool. That's actually fairly concrete already. Maybe we can do something interesting with that, right? And then the engine looks at the next line, and now it's, okay, not really telling you anything, because we know value is positive, but we don't know the concrete number. So yeah, it's divided by 10. It's still positive, I guess. But besides that, not much information has been learned. And now the critical part. We get to the first condition, or the first if statement, I should say. And that if statement checks remainder. and now remainder is remainder equal or greater 5. And in this universe that the engine is looking at right now, the assumption is that value is positive, and therefore the remainder must be between 0 and 9, right? And well, 0 and 9 can be greater than 5, but doesn't have to be. So again, the engine is like, it's a condition, it could be true or false. Let's just make an assumption. Let's say it's false. Okay, if it is false, remainder is smaller 5, so, but it's still between 0 and 9, so it must be between 0 and 4. Okay, and the if is of course not entered, so the engine jumps to the end and sees, okay, method is complete here. That's just a state. Okay, interesting. We have a final state. Remainders between 0 and 4. We return a positive number. And yeah, okay, maybe nothing too interesting if we only look at this universe, but maybe there's something else. So let's create an alternative universe. And in this alternative universe, we took a step back and take a different branch. And we say, well, the condition in the first if in line 8 is actually false this time. It's the remainder, it's actually true this time. The remainder is not smaller than 5, but equal or greater than 5. But we're still in the universe or under the assumption that value itself is positive. So the remainder must still be between 0 and 9. So, well, if it is equal or greater 5, it must be between 5 and 9, right? And this also means that we enter the if, and now we take a look at the inner if. And if we take a look back, we stated or we figured out that in this universe, f positive is actually true. So we go here, we increase value by 1. Again, that doesn't help the engine too much. It knows value is positive. Now it's 1 bigger, still a positive number. Not too much interesting happening here. But okay, method is complete and returned a value that is 1 bigger than what the original value was or what the value was before here. And the remainder must be between 5 and 9. And again, looking at this, it looks fine, nothing crazy to find here. But we still have another branch that we didn't explore, right? So the engine takes a bigger step back and says, okay, create another alternative universe where value is actually negative. And then we do the same thing again. We step through the code and try to figure out what are the consequences of this assumption. So the assumption is value is smaller than 0. The first result, of course, is this condition becomes false, and therefore f positive gets the value false. There we go. Clear. And now the crux, right? The engine, of course, knows how the modulo operator works in C#. So it knows value is negative here, because that was the assumption that was taken a moment ago. And therefore the remainder must become negative. So it must be between -9 and 0. Because, well, we do modulo 10 and the input value is negative. Okay, cool, sure. Let's go on. Next line, again, not super interesting. Value is negative, we divide it by 10, it's still negative. We don't really learn anything. Let's move on. Let's get to the if statement again. And here, the interesting thing happens, right? Remainder is between -9 and 0. But the condition is remainder must be equal or greater 5. Well, that's of course always false. If the remainder is negative, it cannot be equal or greater 5. So the engine is like, this is not even a condition. This is under the assumption we've just took that value is negative. This is always false. We just jump to the end and we're good. Done. And now you can see, and the engine will figure this out as well, there's something missing. If you're looking at the lines here which represent which universe covers which path of the code, there's a gap here. And there's a gap here because this is never reached in none of the universes. And that is because there's a universe missing. The developer who wrote this code intended there to be a fourth alternative universe, which of course is, well, value is negative, but remainder is equal or greater 5. But that is a contradiction because of how the modulo operator works, right? And creates a negative remainder. And therefore, this is never reached. And this universe over here just doesn't exist. And the engine doesn't really know which universes are supposed to be there, of course, but it knows a few things, and it knows, for example, which part of the code has been covered. And it also knows what were the results of all the conditions. So what it does is it takes a look at the condition at line 10 and says, in each of the universes where this line was reached, which was only one, it was only reaching one, and in this universe, well, the result was true. There is not actually a point in having this condition in the first place because, well, it will never be false. There's no point in having this. And that's exactly what the analyzer is pointing out. It's saying, change this condition so it does not always evaluate to true. Some code paths are unreachable. And this is, of course, more a consequence of the core of the root problem, but it points you in the right direction. Wait, why is this always positive? And this is what the analyzer finds, right? It says, change this condition so that it does not always evaluate to true. Some code paths are unreachable. And of course, this is more like a consequence of the root cause of the problem, the root cause being that the return modulo 10 for negative values is negative. But it points you in the right direction because it says, hey, this code doesn't really make sense. There's some structural problem with it here. Take a closer look. And this will allow you to find this bug. And it's not the only kind of thing that the engine can detect. There are multiple other things it can find. It can find possible null dereferences, so all the pesky null pointer exceptions you might have in your code. It can take a look at index out of bounds problems. It can take a look at integer overflows. All these things can be found and detected with symbolic execution. And this is, in my opinion, is one of the most interesting and powerful analysis techniques that we use at Sonar. And it found me a lot of, like, it doesn't trigger too many things usually. Well, sometimes it helps you a bit, like finding some unneeded code or something like that to simplify. But once in a while, it finds these really, really brutal bugs like this one. And then it's like really shines and has a lot of value. And I find this is really cool, and it's my favorite analysis technique. And I hope that was insightful for you. Of course, a bit technical session, but I hope you could follow along and learn something interesting. And if you have any questions about symbolic execution, feel free to shoot me an email at tim.pullman@sonarsource.com. And thanks a lot for watching.